Hello, welcome back. So hope you have a rest yesterday, Sunday. And yeah, today we are very happy to have Tamara Broderick with us. She did her PhD in Berkeley and also spent some time in Europe before, and now is a tenure track in MIT. And is an expert in nonparametric Bayesian statistics. And actually, is when we thought about inviting her, was also because we heard that her lectures in the MLSS in previous one were amongst the most rated ones by students. So here is the pleasure for you. And yeah, I hope you all enjoy her talk.
Thanks for the introduction. That's a lot to live up to, but hopefully I will. So today I'm really excited to talk to you about non-parametric Bayesian statistics. And I think when you first hear these words, you sort of automatically think, oh yes, Bayesian statistics with no parameters. But I want to immediately tell you that's the wrong thing. It's actually the exact opposite. Somehow, and we're going to see exactly how this is true, non-parametric Bayesian means Bayesian statistics with a massive number of parameters. In fact, an infinite number of parameters if you look at it in one way, and a growing, always growing number of parameters if you look at it in another way. And we're going to make these ideas precise throughout this series of 3 lectures this morning. But let me first start by giving you sort of an overview, a taste of the ideas that we'll be talking about. Okay, so I've said, non-parametric Bayes, it's sort of a tautology that means Bayesian statistics that is not parametric, but as I said, there's a little bit more to it than that, and we really want to dissect what the meaning of that phrase is. So in particular, let's talk about, there are 2 parts to this, non-parametric and Bayes, and in particular, Bayesian statistics is going to be a really fundamental part of these lectures. And so what I mean by Bayesian statistics is that we're going to have some model for our data, and it's going to depend on some parameters. Since we don't know those parameters, we're going to put a prior distribution over those parameters. And then we're going to use Bayes' theorem in the end to get out a posterior of the parameters now that we've seen the data. So this is sort of our belief going into the experiment. This is when we collect the data from the experiment. This is our belief at the end of the experiment about the unknown parameters. These are the things that we're trying to learn about. Okay, and so the non-parametric part of this is that we're going to have a Bayesian model, but somehow there's going to be an unbounded, growing, infinite number of parameters. And again, this is the kind of statement that might seem fuzzy at this point, but by the end of these 3 lectures, it should be really clear in your mind what that means. But to get an idea of what's going on here, let's go through a few examples. An example I like to start off with is what I like to call the Wikipedia phenomenon. So I have a friend who does her research in tropical geometry. And actually recently, she loves tropical geometry so much that, true story, she got a tattoo of some tropical geometry construction on her foot. And so she's my friend, I was really curious, what does this construction even mean? And so I go into Wikipedia and I'm looking up tropical geometry, and this leads me to articles about algebraic geometry, and I just keep reading on Wikipedia more and more articles until I'm reading these esoteric articles about things like the Pacific Crest Trail, which is this trail that goes from the north to the south in the United States of America. It's extremely long, like 2,600 miles. And so the point of this story is that you get on Wikipedia and you can just keep reading articles forever, and no matter how many articles you've read, somehow there are always more topics or themes that you can discover. And so this is going to be the idea of the growing number of parameters, that there's some sort of latent set of parameters, like topics or themes in a textual corpus, and there are always more of them to discover as you get more data. And we see this in all kinds of other data domains that are not just text. So for instance, I don't know if you can see this that well, but this is what's known as a flapjack octopus. It's a particularly cute form of octopus. And so a fascinating thing about species is that, we've been looking as humans for new species for just an incredibly long time, well over hundreds of years. And we still discover new ones every day. So I looked on the internet this weekend, and it turns out in the last week somebody discovered a new wasp and named it after Brad Pitt. And you'll find that no matter sort of what weekend you look on Google, there's always some new species that's been discovered, even though we've discovered so many species. Now, the wasp wasn't really photogenic, so I kept up this flapjack octopus, which was discovered in like the last year. But this is the idea again that somehow we're just always discovering new species. There are always new species to be discovered, and so there's this growing number of sort of things that are going on. In a slightly more abstract version of this, we can look at density estimation. So if I have a set of data points, I could estimate that those data points come from some parametric model, some model with a fixed number of parameters. But instead, I might estimate that they come from a model where the number of parameters can grow with the size of the data. That as I get more data, I can estimate more and more complex, wavy, unusual densities for that data. This comes up in survival analysis. Again, I might estimate more and more sort of unusual and complex survival curves. Even something like exercises. So maybe I'm looking at people's exercise routines. And the more people's exercise routines I look at, the more that I'm able to discover new, different types of exercises that I had never known to exist before. We can look at this in genetics. So if we look at more and more people's genetic code, we might discover more and more ancestral populations that we hadn't known about before. We can look at this in this really fascinating study on newborn health. So here the idea was there's this hospital, we're looking at newborns that are being born in the hospital, and we might expect to see more and more different types of health issues in those newborns as we study more and more of the newborns. And in general, you might expect to see more and more different unique health issues in any sort of population, even an adult population, some population that you're studying in a medical field. In graphs, in social networks, you can imagine, on Facebook, on Twitter, whatever social network that you subscribe to, there are going to be more and more different types of social groups, more and more different types of latent interests that you might discover in that graph as more people join that social network. Images, you might have a collection of images, and you might discover that there are more and more different latent objects in those images. I mean, we know where the objects are, but for a computer, you want to be discovering these objects, and so you want to have the option to say, oh, there are objects that I haven't seen before. New objects to be discovered all the time. And so the fundamental idea of Bayesian nonparametrics, and again, we're going to make this much more precise as we go on, is that somehow, I have some finite data set. Maybe it's a collection of documents on Wikipedia. And in that finite data set, there's some finite number of latent variables, something like the themes or topics in my documents. And by having an infinity of latent parameters sitting around somewhere, I can always draw on those latent parameters, the parameters I haven't seen yet, to get more and more topics as I get more and more data. So again, this is pretty abstract at this point. We're going to get into details pretty quickly. But before I do that, let me talk about one other motivation for nonparametric Bayesian statistics, and this one's a bit more theoretical. Yes? I'm sorry, I couldn't hear the question.
The slides are on the internet already? Or?
So I'm going to put the slides on the internet after the talk. In part because I'm going to ask you some questions, and I don't want you to already know the answers. Okay. Okay, so here's another set of motivations for Bayesian nonparametrics, again, somewhat more theoretical. Okay, so imagine that I have some sequence of data. So these might be things like documents in a corpus. So maybe I have my first document that I scraped from Wikipedia, my second document that I scraped from Wikipedia, and so on. And so let's call that X1, X2, X3, document 1, document 2, document 3. Then we say that our sequence of data, could be any sequence, we're just thinking of documents for the moment, is infinitely exchangeable if for any finite number of data points, I could have interchanged those data points, and the distribution over them wouldn't change. So somehow we're fundamentally assuming here that our data are randomly generated, and we're modeling our data somehow with a distribution, that's this P of the data. Sigma here is a permutation, so it permutes the indices 1 to the n to another order of those indices, and we're saying that no matter what n I choose, that these distributions will always be the same, and then my data is infinitely exchangeable. And somehow this just represents, I think, some kind of intuitive notion we have about data, that, if I run my analysis on Wikipedia documents, I have some machine learning statistics analysis that I'm going to run, I don't think that it should really matter if I scrape them in one particular order versus another particular order. You can also think of this as somehow fundamental to science, that, I don't think that if I did my experiment tomorrow instead of today, that it should really change things. And I'll just note that this is a much weaker assumption than something like independence and identical distribution. If I have IID data, then it will be infinitely exchangeable. But if I have infinitely exchangeable data, it need not be IID. Okay, here's the strength of this weak assumption, though. At this point, this seems like a pretty weak assumption, but what does it tell us? It tells us that Di Finetti's theorem holds. that if I have a sequence of data, again, x1, x2, x3, x4, these are sort of, the documents in my corpus, say, then it's infinitely exchangeable, this weak assumption that I think we're pretty willing to buy most of the time, if and only if the following is true. If I can express the distribution over my data, I can say that my data has the same distribution as if there were some new parameter theta that I didn't know about before, it's potentially random, and I draw my data independently and identically conditional on that theta. Okay, here's what's interesting about this theorem for our purposes. One, it motivates, in some sense, statistics. It motivates that parameters even exist. So we didn't assume any parameters, sort of, don't look at this part for the moment. All of the assumptions we made were just that there's some distribution that randomly generates the data, and Pau, Di-Finetti's theorem tells us that we get a parameter theta. Not only does it motivate parameters, it motivates likelihoods, that there's some probability of the data given theta, any particular data point given the theta. Moreover, it motivates priors and Bayesian statistics. There's a distribution over this parameter theta. That's a fundamentally Bayesian idea that we have this distribution, we have our likelihood, now we can calculate a posterior. And finally, it motivates non-parametric Bayesian priors in the following sense. This theorem would not be true if I restricted myself to finite dimensional theta. And so in order to have the full generality of the Di-Finetti theorem, I need to have infinite dimensional priors and therefore non-parametric Bayesian statistics. So Di-Finetti did a lot of work on this in the 30s. It's really amazing stuff and it's really fascinating to read. Ewan Savage sort of completed and came up with the general version of the theorem that we think about today and use today. And if you're really interested in sort of this area and getting deeper into the math that's involved here, I'll recommend this Aldous manuscript from 1983, which is just a really fantastic read. It goes deep, deep dive into exchangeability. Yes?
So how can you do it if you go like this if theta is not minus three-dimensional? I mean, what does that even mean?
Right. Well, how about this? How about we start talking about some infinite dimensional things and get down into the details, and then we'll see what this means. I mean, there's some sense in which I don't want to get too deep into measure theoretic concerns. If you are interested in that, though, I will definitely recommend the Aldous manuscript from 1983. But for now, I want to focus on something more practical and start getting into real models so you can see what this means sort of in practice rather than at a really abstract level like here. Yeah?
You mentioned about this infinite trend-wise is more general than but could you give me some more insight about how this is more general than
Okay, so as an example, suppose that I have some x and it's generated normally, so let's call it x0. And then I have x1 to x2, x3, x4, and those are generated IID. Now add x0 to all of them, that's exchangeable but not IID. Okay, this slide is pretty abstract. Let's start getting into more detailed, concrete things that you could use in real life as a model. Okay, so where we're going to be going with this. So when people talk about Bayesian nonparametrics, that's a huge field, there's a lot going on in it. But somehow, if you want to read papers in this field, if you want to work in this field, if you want to understand what's going on in this field, you're doing pretty well if you understand what the Dirichlet process is. And so I'm going to focus a lot on building up intuition for the Dirichlet process, talking about the generative model for the Dirichlet process, and at the end of this, I think we're going to have a sense of this question that I sort of posed in the beginning of what it means to simultaneously have a growing yet infinite number of parameters in non-parametric Bayes. And so in that sense, you can think of the Dirichlet process as sort of this microcosm for all of non-parametric Bayes. That's this particular example that'll get you the main idea, and then you can go out in your own life and find out other models that people use in practice, and I think it'll be relatively easy at that point for you to pick them up. In the same way that you learn one programming language, and then it's easier to pick up future programming languages. You'll often find that people say something like, the Chinese restaurant process. That's basically the Dirichlet process, but not really. At the end of this lecture, at the end of, well, maybe the next lecture, you'll have a sense of what that means as well. How is the Chinese restaurant process the same as the Dirichlet process, and how is it actually different? And why do we care? And why do we even want these two different processes? We'll talk about inference. So these are generative models. Again, in the Bayesian framework, we start by building up these generative models, and then we use them to go and do Bayesian posterior inference. So we'll talk about how to do that. And then hopefully, with enough time, we'll get a taste of what else is out there in Bayesian nonparametrics besides these processes. Okay, so without further ado, we're going to start on building the intuition towards the Dirichlet process. So even if some of this stuff is review, I just want to make sure that you're completely ready and on your toes to deal with it, so that when we get to the Dirichlet process, everything fits together perfectly. Now, the Dirichlet process is a particular example of a Bayesian nonparametric model. The Dirichlet process is often used in combination with other likelihoods to build up models in Bayesian statistics. And so I'm going to choose a particular combination of the Dirichlet process with a likelihood in order to build up our intuition about the Dirichlet process. And so, in particular, as an example going forward and throughout the rest of this particular lecture, I'm going to be thinking of mixture modeling. And I'm going to start off with a finite dimensional mixture model. So we're going to do a finite Gaussian mixture with two clusters. So there are obviously two clusters here, and the idea of the inference here would be that you would just want to find these two clusters. And again, what we want to do is we want to build up a likelihood, we want to build up a prior, and then at least theoretically, Bayes' theorem would tell us immediately how to get a posterior that expresses our knowledge about the unknown parameters after we've done it. Okay, so let's build up our likelihood first. Well, our likelihood will do something like say, okay, each data point belongs to one or the other cluster. There's some probability rho 1 that it belongs to cluster 1, some probability rho 2 that it belongs to cluster 2, and this will be the indicator of which cluster the data point belongs to, so it's 1 with probability rho 1, and 2 with probability rho 2. So maybe this will be 0 to 1, the 0 to 1 interval, rho 1 will be some fraction of that, rho 2 will be the remaining fraction, and they add up to 1. Likewise, we're going to draw the actual data values. We'll say that they are normally distributed around some mean that's specific to each cluster, and with some covariance that's just some covariance. Here I'm fixing the covariance, you don't have to. It's just a lot easier for me and a lot easier for the slides and the math. Okay, so there's going to be some mean for cluster number 1, some mean for cluster number 2, and then we draw the data independently, conditional on the z's and the mu's around that. Okay, so this is our likelihood at this point, but we're Bayesian, so we want to put some priors on the parameters. In particular, gosh, I don't know, going into my problem, into my mixture model problem, what proportion of the data is in each clusters, so I want some prior on that. I don't know what the means of the clusters are going into my problem, so I want some prior on that as well. So in particular, I don't know the means, I need to put some prior on it. A particularly convenient prior because it has a lot of nice conjugacy properties and it'll be easy to work with in practice in terms of deriving posterior calculations would be the choice of a normal. So we have another normal with some mean and some covariance. We don't know rho 1 and rho 2. It turns out for similar reasons, for conjugacy reasons, because it'll be easy for calculating, we might choose a beta distribution. So here the beta distribution is a distribution that gives you a number between 0 and 1, and then we'll just say rho 2 is 1 minus that first number. And so what this ends up looking, and I'll just say quickly, so our inference goal again is the assignment of data points to clusters. We want to know which data point is in each cluster, because originally we just see the data points. We don't see any of this other stuff. We have to infer it. And we want to know the cluster parameters, like the means of the clusters. And so the generative model here, if I just started off from the beginning and sort of ran through it, would look like so. I would first generate my proportions of data points in each cluster. I would generate the cluster means, and then I would generate the data around the cluster means. And so what I want to do now is get you very, very familiar and feeling really awesome about the beta distribution and its cousin, the Dirichlet distribution. Okay, so the beta distribution, this is the form for its density on the interval 0 to 1. So rho 1 has to be between 0 and 1. It's a frequency, and these hyperparameters A1 and A2 have to be greater than 0. You'll see this gamma function appears here. The main thing that you want to know about the gamma function is that it behaves like a factorial. So if it has an integer argument, a positive integer argument, then its m plus 1 is like the m factorial. Gamma of n plus 1 is like n factorial. And in general, if I have any positive argument, again, it kind of behaves like a factorial. Like I take x out and multiply by gamma x. And that's all you really need to know about the gamma function. It's like some sort of binomial coefficient here. so let's think about what happens. For instance, let's say that I set A1 and A2 to 0. What density is this? Yeah, it's uniform density, right? So if I put A1 to 1, A1 to 1, then these become something to the 0 power, something to the 0 power. So this whole thing is proportional to 1, and I get the uniform density. On the other hand, if I set my two parameters, A1 and A2, to something larger than 1, to 2 and 2, I get something that seems to be peaking more around 0.5. If I get something where I set my gamma parameters to, my beta parameters to less than 1, like 0.5 and 0.5, then I get something that tends to peak more around 0 and 1. And I can also set them to be different values, 2 and 5, in which case I get something like this. Okay, so let's say that I take both of my parameters of the beta distribution to be the same, and I'm going to make them very, very small. So I'm not actually going to take them all the way to 0. I'm going to take them close. I'm going to make them very, very, very small. Then what do I expect those distributions to look like?
Two directions.
Yes, I expect there to be a lot of peaking around 0 and 1 and very little mass in the middle. Likewise, if I make them very, very large, what do I expect to happen?
One peak at 1/2?
Yes, I expect to see the peak going up at 1/2. So let's look at what this actually looks like in a demo. Oh, and actually, last one. What if I have A1 greater than A2? Which one's going to be bigger in general, row 1 or row 2? Feel free to shout it out or raise a hand. Row 1, yes, great. Okay. Now, sometimes it's hard to really look at these from a density point of view, so let's just look at them, actual draws of this in practice. Okay, so here what I'm doing is saying that I'm going to make a bunch of draws from the beta 1, 1. So we agreed before that this was the uniform distribution, right? What that means in particular is that row 1 here, so I'm plotting here row 1 and I'm plotting here row 2, row 1 is going to be uniform. So it's not like I'm actually, I'm drawing a random distribution here. The random distribution itself isn't uniform. It's row 1 that's uniformly drawn. And so if I make a bunch of draws from the beta 1, 1, this is what it looks like, sort of all over the place. Okay. And now I can do the same thing. I can say, okay, what if I want to have a bunch of draws from something that's near 0, and for near 0, I'm going to choose 0.01. Well, as we said before, the mass goes all to the edges, to 0 and 1. And so if I make a bunch of draws from the beta 0.01, it's almost certain to be all of the mass at one or the other, either row 1 or row 2. And then finally, I can do that third option that I mentioned. What if I choose the beta parameters to be sort of, going to infinity, getting very large? Well, if I have them getting very large, all the mass and the density is near the middle, which means that the random distribution that I'm choosing is actually uniform. And so when we make a bunch of draws from this, we get this sort of close to uniform random distribution. So again, what we're drawing all the time here is actually itself a distribution. It's a random distribution. Are there any questions about this? Okay, great. So we're familiar with the beta distribution now. Saw some demos. I'll also put the code online. Another important thing that we want to know about the beta is that it's conjugate to the categorical. So again, the categorical distribution is this draw where I say that I draw 1 with probability rho 1, 2 with probability rho 2. And so I have my beta prior here, my categorical likelihood for an indicator variable z. And if I want to calculate the posterior, then what I'm going to do first is calculate the likelihood, the joint distribution between rho 1 and z. So that'll be the likelihood, rho 1 to the indicator variable z equals 1. So this 1 is an indicator variable. It says that we put a 1 in if z equals 1 and 0 otherwise. And 1 minus rho 1 to the indicator variable that z equals 2. And then we put in the prior, the beta distribution prior, and in this proportionality constant, I have everything that doesn't depend on rho 1 and z. So, all of these gamma functions and everything, I've left them out because they're not important for this calculation. Okay, so now this tells me that if I have rho 1 given z, that's going to be proportional to the same thing, which will be rho 1 to the a1 plus this indicator variable minus 1. 1 minus rho 1, I'm just taking the thing above and putting it below and recalculating. And the important thing to notice here at this point is that this is the kernel of the beta distribution. That is, it's an unnormalized beta distribution. And so when we normalize it, the result is a beta distribution. So why is this important? Well, in general, conjugacy is important because it lets you get around the difficulties of using Bayes' theorem. In general, with Bayes' theorem, you have this prior, and you have this likelihood, and then you say that your posterior is proportional to that. But hidden in that proportionality is that you have to divide by your prior times your likelihood and integrate out your data. Integrate out your parameter. No, it's your data. No, it's your parameter. Parameter. There's an integration is the important part. But the thing about that is that integration is difficult, right? Like, that's the whole point. We don't want to do integration. Maybe it's fine in a few dimensions. But as soon as you get to high dimensions, and we're going to be getting to very high dimensions, you don't want to do integration. And so here what we've done is we've totally sidestepped integration. We've said that all we had to do is we had to take the parameters that we started with here and do an addition to get the posterior. Instead of doing an integration, we just had to do an addition. And so this is much easier. Instead of having to do something like Markov chain Monte Carlo or variational Bayes or anything like that, we got to do addition, which is the easiest thing you can do. And so something you want to think to yourself, if it's not immediately obvious, is what this would be if we had n more data points. Okay, so that's the beta distribution. And that's what we would use in the case of a two-dimensional or a two-component mixture model. But of course, in general, we don't just have two components. What do we do if we have more? Let's suppose now that we have k clusters, and for the purpose of my illustration here, I'll suppose k is 3, but in general, we might have k. Okay, well, we're going to do the same thing. What's our generative model? It'll be the same thing that we had before. But now instead of a beta, we're going to need a distribution that gives us numbers between 0 and 1 that add up to 1 and gives us k-such numbers. So that's the Dirichlet distribution. So in particular, we'll take the draw from the Dirichlet. It'll be 3 numbers that add up to 1. We're again thinking of this as the interval from 0 to 1. The next thing on our generative model is for each of 1 to k, we'll make a draw that'll give us the cluster center. Now, for each data point, we'll decide which cluster it comes from by drawing from the categorical distribution. And then finally, we'll draw the actual data point itself around the data center it belongs to. And so again, what we're going to do is spend a little bit of time getting familiar with the Dirichlet distribution. Are there any other questions before I go on with that? Okay, so let's become Dirichlet distribution experts. So something that you want to convince yourself of with this Dirichlet distribution density is that it reduces to the beta distribution density when k is 2. Also, I'll just note that this density is over the space where the rows are between 0 and 1, so they actually are probabilities or frequencies, and they sum to 1, so we would call that the simplex. Okay, so again, we want to ask, what does this look like? Well, when AK equals 1 for every K, we again see that we have rho to the 0. All these multiplications of rho to the 0, so we're effectively saying our distribution is proportional to a constant, so we have a uniform distribution. When AK is less than 1, so maybe all 3 of my AKs are 0.5, then I can plot that, and let me just say for a moment when I'm plotting here, I'm plotting rho 1 and rho 2 and the density, and the reason I'm not plotting rho 3 is because it's defined by rho 1 and rho 2. It's just 1 minus them. So we completely know what rho 3 is once we know rho 1 and rho 2. Okay, so once we have that, and we have a bunch of A's that are less than 1, we can see we're getting the same behavior we saw before. We're getting sort of the mass at these edges. And not just at the edges, even at the vertices. In the case where all of the numbers are greater than 1, we're starting to see peaking in the middle. And in the case where we have some other combination, then we see peaking in a different direction. And in particular, since A1 is greater here, we see that it's greater towards rho 1. Okay, so we can again ask, what happens as all of the A's become very, very small? And again, we see that, or I hope that you can believe for the moment, and we'll see a demo in a second, that all the mass tends to go at one of the rho values being very large, or being near 1. And same thing as we have all the A's being equal, and they're getting very large, we have that all of the mass is going towards all the rows being equal. Okay, so let's see this in action. Okay, so what I'm drawing here is a Dirichlet where all of the A hyperparameters are equal to 1. They're all equal and they're all 1. And I'm making a random draw from that. So it's going to be a distribution over the integers 1 through 4. A random distribution. And so can anybody tell me, is the distribution, so when we talked about the beta, rho 1 and rho 2, we said that in the case where all of the A's were 1, that the distribution on row 1 was uniform. Is that the case here? I see some various heads. Can somebody say yes or no and say why? So is row 1 uniformly distributed on 0 to 1?
Yes, because it varies from
Does anybody have an alternative viewpoint?
It's not uniform because it's less likely to be very big because that would imply that all the others are very small together.
So they are all simplex.
Yes, here we go. So this is the point. So this is a tricky thing, and it's good to keep in mind. When we have the A's all equal to 1, what does uniformity mean? It means uniformity on the simplex. And so in the case where we were talking about the beta distribution, that was just uniformity on 0 to 1. Now we have uniformity on the simplex, so row 1 isn't just uniform on 0 to 1 on its own. And so we can make a bunch of draws from this. And you can sort of see this behavior in action. In general, they seem to be sort of lower, right? Okay, let's try another one. Now we do the same thing that we did before, where we take all the A's equal to 0, like we did for the beta distribution. Well, we take them very small. We don't take them to 0, but we take them very small. And you see again this behavior where when you have these very small hyperparameters and they're all equal, that one of these row 1, row 2, row 3, row 4 is chosen to stand out, to be the big one. And so every time this is changing, I'm just making another draw from this distribution. Okay, so that's very small A's. Now let's try very large A's, and it's what we said happened on the previous, when we were looking at the actual slides, that it looks like we have a uniform distribution, and again, there's this distinction. We're saying that we're drawing a distribution randomly using the Dirichlet. That distribution that we're drawing, in this case, when all of the A's are very large, is itself uniform or nearly uniform. So I can make a bunch of draws from this distribution, and they all look pretty close to uniform. And another thing to notice here is that uniform here means 1 divided by the number of these. So these are all at around 0.25 because there are 4. Great. Okay, any questions on this? Okay, and another point that I want to make is just as the beta was conjugate to the categorical, so it gives you a distribution, and then when you draw from that distribution, the posterior of that distribution is again beta. In this case, the same thing happens with the Dirichlet. So if I draw my rows from a Dirichlet distribution with parameters A1, A2, A3, A4 to A capital K, so that, by the way, this is what this notation means. It means that I'm just taking this vector A1 dot 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 to A capital K. And if I now draw my z from the categorical of that, so it's 1 with probably row 1, 2 with probably row 2, etc., then I can check, and if this isn't clear to you, I definitely recommend just writing it down and doing it, and I definitely believe that you can, that the posterior probability of these frequencies, of these probabilities, is Dirichlet distributed. And this is much like we had in the beta case. The updated parameters, these are the updated parameters, the posterior are the original parameters plus 1 if we happen to draw k. So only one of the parameters will be incremented by 1 for this data point. And if I make a bunch of z draws, you want to convince yourself what happens then. What would that posterior look like? So think about that. Okay, so at this point we talked about a mixture model for 2 clusters. We put up the whole generative model. We said how we might generate that in a Bayesian framework. The things, the parameters we might be interested in, the proportion of data points in each cluster, the assignments of data points to clusters. And so now we've been talking about K, some capital K, and there's nothing specific about this capital K. I didn't say, oh, capital K has to be very small, it has to be very large. It's just any K, it could be greater than 2, could even be 2. Everything, still holds on this slide. But technically speaking, when I drew this cartoon where I had 3 clusters, like here's a cluster, here's a cluster, here's a cluster, I was kind of implicitly assuming something about K. Now let's think about K being greater than the number of data points. How would my cartoon change? What would be wrong about my cartoon where I have, here's cluster 1 with some data points in it, here's cluster 2 with some data points in it, and here's another cluster with some data points in it, and all the clusters look like that. What would be wrong about that cartoon in this case?
You wouldn't have points for all the clusters.
Yes, exactly. There will be clusters that do not have points in them. Okay, so let's think a little bit more about this case. So, I've been drawing this cartoon of the unit intervals from 0 to 1. And I've been saying, okay, we have these probabilities of the clusters, and they add up to 1. And so I can draw them as these subintervals within the unit interval. So here I'm just putting dot, 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 so I don't have to draw all 1,000 of them. But I will draw all 1,000 soon. And so in this case, if I have, say, like 20 or 30 data points like I did on the previous slides, then there's just no way that I can fill up all these clusters. And this represents some very real data scenarios that we might encounter in real life, some of which we've mentioned so far. So let's say I'm looking at species. I go out into the world and I'm looking at all the animals out there and I'm trying to count the species and I'm finding new species. Well, the fact is, we have not found all the species yet. As I mentioned in the beginning, I'm willing to bet you a lot of money that there are more species out there still. There's a finite number of species on the Earth. There's not an infinite number, but we definitely haven't reached it. Topic modeling. We're going out into Wikipedia. We can imagine that, well, there's probably a finite number of themes on Wikipedia right now, but we certainly haven't reached them all if we've read 100 articles, 1,000 articles, 1,000,000 articles. And certainly, even if we've read all of Wikipedia, we haven't reached all the themes that are out there in the world. Groups on a social network. Yeah, there's probably some finite number of groups that people can form, but we certainly haven't reached it yet. And so we want to understand, what's the behavior that we see in these cases, which is a very different kind of behavior than the mixture modeling that we've been looking at so far. Okay, so in order to do that, we're going to start making a distinction in our nomenclature. We're going to say that there are two different words now. One is a component. This is the number of latent groups. So here there's 1,000 latent groups. There's 1,000 possible clusters. All of these could be clusters if I had enough data, but I don't have 1,000 data points yet. And so we'll call clusters the number of components that actually have a data point associated with them. So in our generative model, let's say that we're drawing data points. We're saying, oh, I'm going to draw from this distribution, row 1 to row 1,000. I'll choose 1 with probability row 1, 2 with probability row 2, etc. After 100 data points, there will definitely be less than 100 clusters, even though there's still 1,000 components. Okay, so let's look at a couple of demos. Okay, so what have I drawn here? Well, first of all, again, we're seeing the unit interval from 0 to 1. And I made a draw from a Dirichlet distribution. Now, before we had k equals 2, and we had k equals 4, and now we have k equals 1,000. Now, you're not seeing 1,000 lines here because some of these probabilities are just so thin that they appear as the same line on the screen, but they're all there. There are actually 1,000 of these intervals that add up to 1. So does everybody get what's being shown here? Clarifying questions in general, by the way, are super welcome. Yeah?
So if you have lines like that of 8 more than twice, don't they end up more than 1?
I'm sorry, what was the question?
Each line represents one of
So the way that I'm plotting this is like I had on the previous slide, where I say, okay, I'm going to plot 0 to row 1, then I'll plot row 1 to row 1 plus row 2, then I'll plot row 1 plus row 2 to row 1 plus row 2 plus row 3. And so at the end of the day, because they add up to 1, that's what the last line is. Yeah, great. Yeah, great question. I'd love to hear anything else that people might be confused about.
What were the values for A1 to A1000?
Yes, great. So the A's that I have chosen here are all 0.01. Okay, well, if you think of any more questions, bring them up. Okay, so now let's think about how would I draw from this distribution? Well, we talk about drawing from these distributions as I say something like, oh, I'm going to draw 1 with probability row 1, I'm going to draw 2 with probability row 2, but how am I actually going to do that in practice? Well, I hope we can all agree that one way I could do it in practice is I could actually, independently of this, so remember, this thing was drawn randomly, so we have to make sure that we're doing something independently. Independently of this, we could draw a uniform random variable. I'm going to draw a uniform random variable. So that's what this red triangle here is. And so because the length of this interval is exactly, row 256. I mean, I don't know exactly what index it is, but it's one of the rows. That uniform random variable will belong to that interval with probability equal to row 256. The uniform random variable will belong to the interval row 1 with probability equal to row 1. And so this is a way to choose from this distribution. And so what we can think of is, we can think of this as our first data point in the mixture model. This data point belongs to whatever cluster this row corresponds to. And so at this point, I have 1,000 components and one cluster. Again, any clarifying questions are welcome. And so what I can do is I want to keep drawing the assignment of data points to clusters. So I'll do this for the second random variable. So I draw another uniform random variable. I'm doing these IID across the data points. So this is data point 2. I'm doing them independently of the original Dirichlet draw. And now it turns out that I have two clusters. I belong to a second cluster here, one that's different from the first. And I'm highlighting each cluster that I choose in blue. Yes? Yeah, great. Okay, so there's a couple of layers to this question. So one is, okay, so the question is, if I have two data points, yeah, so if I have two data points, how can I decide they're from the same cluster and not from two different clusters? And so there's a couple of points here. So one is, at this point, I'm just exploring a generative model. And so if you were actually doing posterior inference, this is a question that we'll get to later. How do you know which data points are actually in the same cluster and which are different? And this is definitely a real problem that comes up in posterior inference. I'll also answer it on the level of the generative model in the sense that I absolutely could have chosen a uniform random variable in this region, and then this would still be highlighted. So right now in the illustration, I'm just highlighting every region that I put any data point into. Does that answer the question? Okay, great. So I can keep doing this. Draw a third data point, I draw a fourth data point, I draw a fifth data point. I just keep going on and on. You can see the number of data points I've drawn at the top. So K is the dimension of the Dirichlet distribution, N is the number of data points that I've drawn. And it seems like it's filling up the clusters pretty quickly from this perspective. I mean, certainly we've gotten by 91 data points to most of the maps of the unit interval. But it's hard to say how many clusters I've actually filled up, because I mean, there's actually 1,000 components here. And I know that I haven't filled up more than 91 of them. And so a lot of these small components are not getting filled. They haven't been chosen yet. And so in order to get a sense of how the number of clusters is actually growing, I'm going to give a second illustration. But are there any other questions on this one before I move on? I can always go back to the previous illustration too if there are questions. Okay, so let me tell you what's going on here. Oh yeah.
I think you can explain how to draw samples from the categorical series. I'm just curious.
Yeah. So let me be more careful about that. So the question was, how do I draw samples from the categorical distribution?
How it's the form. Can I pick up from it?
Oh, okay, so the analytical form of the categorical is only exactly this simple form, which is I draw the index 1 with probability row 1, I draw the index 2 with probability row 2, I draw the index 3 with probability row 3. That's it. It's a super simple form. Another way that I could write that, and I wrote this on a previous slide, is I could say row 1 to the indicator, z1 or z equals 1, row 2 times row 2 to the indicator, z equals 2, etc. And so the way that we drew from the categorical in the previous slide was we said, hey, we're going to make this interval, this unit interval, by putting row 1, an interval size row 1, then an interval size row 2, then an interval size row 3, and then just put down a uniform random variable. And since I know that uniform random variable will be in the interval of size rho n, with probability equal to rho n, that's like drawing from the categorical. So what we were doing, in fact, was drawing from the categorical. Great. That's great. Any other questions? Okay, cool. Okay, so let me explain what's going on here now. So great. So we definitely want to know what was going on in that previous picture because this is just going to be building on it. So in the previous picture, I was drawing from a categorical, as was just said. I had this categorical distribution over 1,000 possibilities. And that those 1,000 possibilities were drawn from a Dirichlet distribution. So I've done the exact same thing here, I'm just not showing you. So secretly, over here, I have my Dirichlet distribution that I'm going to be drawing from. And I'm going to do the same thing I did before. I'm going to put down a uniform random variable, and I'm going to say that that data point corresponding to that uniform random variable belongs to the cluster it falls into. And now here's what I'm going to do. On here, I'm going to index the sample. So each uniform random variable will make me hop by 1 here. So this is the first uniform random variable. When I get to the second uniform random variable, I'm going to go here. And the third one, I'm going to go here, and so on. So these are the uniform random variables that I drew before. They're equivalent to sort of like the data point assignment to a cluster. And what I'm going to draw on this axis, which unfortunately is getting a little bit cut off here, let me see if I can just move that over a little bit. Okay, cluster by order of appearance. So what I'm going to do is I'm going to say, so the components have an ordering. You sort of, you know, there's row 1, row 2, row 3, etc. The clusters, I mean, they don't really. So what I'm going to do is I'm going to say that the first cluster I see will be called cluster 1. The next cluster I see that is not cluster 1 will be called cluster 2. The next cluster I see that is not cluster 1 or cluster 2 will be called cluster 3, and so on. And so by definition, data point 1 has to belong to some cluster. That cluster will be called cluster 1 always. But there are 2 options for data point 2. Data point 2 could belong to the same cluster as cluster 1, in which case we'll have a dot here, or it could belong to a new cluster, in which case we'll have a dot at 2. So let's find out what happens. I didn't seed anything in any of these demos, so it's a surprise to me as well. Oh, it belonged to a new cluster. Maybe that's not too surprising. I mean, last time we saw that the clusters had pretty small rows for the choice of A that I chose, and so it's kind of reasonable that this would belong to a new cluster. Okay, so now there are 3 choices. For cluster 3, it either belongs to one of the 2 existing clusters or it starts a new cluster. And we can keep doing this. So far it's pretty boring. Oh, finally we have a data point. Data point 8, it seems, belonged to the same cluster that 7 did. Keep going. And an interesting thing to note about this is we definitely have a lot of data points, even pretty early on, that are belonging to the same cluster as previous data points. But another really interesting thing to note is that the maximum that we've attained so far is the number of clusters. And so in some sense here, we're plotting the number of clusters as a function of the number of data points. And so we see that that number is growing. Seems like it's slowing down a little bit over time. Like it's not growing as fast as it did in the beginning. Some clusters are getting a lot of data points. Some clusters aren't getting so many. You can imagine, these are probably clusters with larger row values, right? And these are probably, the ones with few data points probably have lower row values. And another interesting thing is, at this point, so we have this 1,000-dimensional Dirichlet that we drew from. And we're getting pretty close in terms of number of data points to 1,000. I mean, we're getting like on the order of 1,000. We're not that far off. We're going to get there, sooner or later here. We're not even close to 1,000 in terms of the number of clusters, right? We're not even up to 100 yet. Yes?
But that's the same distribution, so you have A is equal
Yeah.
So if it could be 1, we would see a different picture in terms of.
We would absolutely see a different picture. Could you think about what you think that picture would look like?
We will definitely feel much more clusters up to that point.
Great, so why would that be?
Because they will have uniform probabilities. Well, not uniform, but.
Great, so maybe let's start by thinking about, so let's actually break out of this for the moment. And let's think about what the Dirichlet distribution for 1,000 would look like with A equals 1. Okay, so when we did A equals 0.01, maybe I should actually just remind you of what that looked like first. So we had some very large clusters and some very tiny clusters. And so what do we think about is going to change about this? So I just want to make sure that everybody's on the same bandwidth and everything, following your argument here. What do we think is going to change about this when we go to A equals 1? It's going to be, maybe just say it out loud.
Equal bits, almost equal.
It's going to be more equal bits. They're going to be a lot tinier in general. These are both the points that were being made. So let's check that out. What does this actually look like? And there it is. In fact, the bins are so tiny that it looks like there's just a wall of black, but in fact, each one of these black lines separates a bit. Okay, and so the great point that was made over here is that, well, these are going to be a lot tinier in terms of the rows, and so we're going to be getting a lot more and more rows really quickly. So let's check that behavior out. Okay, so now I'm showing the same graph as before, but here all the A's are 1, whereas before when I showed this graph, all the A's were 0.01. So let's do this again. And indeed, we were seeing a lot of unique clusters for a long time. But we do see some overlap, and I think that you can say we do eventually see some slowing down. And in fact, in both of these cases, in the case where A equals 1 and the case A equals 0.01, I think you can tell me the asymptotic behavior. As n goes to infinity, what's going to happen? How many clusters? I hear a lot of murmurings. Let's just go for it. Somebody. 1,000, yes. K is 1,000. We can't have more than 1,000 clusters. No matter what we do, we're going to get to 1,000. And that's true no matter what A we chose to begin with. Yes?
What is the relation between the amount of data at the mean and the parameter of the Bayesian solution? Because the smaller the parameter, the higher amount of data.
Right, okay, yeah, so the question was, what is the relationship between the amount of data you need and the parameter of the Dirichlet distribution, and K. And the point that I want to make here is, let's say that you don't know K. You don't know K in advance. And I think that would be true of all the examples that we saw. We saw this species sampling example, we talked about topic modeling, et cetera, et cetera. And so let's say you're in a case where you don't know K, and you want to always have this growth. Then it seems like we're in a bit of a bind, right? Because as soon as I choose a K, if I get streaming data, I'm eventually going to hit that K. This is the problem that we will solve with Bayesian nonparametrics. So you have, perfectly anticipated where I'm going with this. Before we go on to exactly that, let me just make a couple of notes here. So one, sort of almost, by sort of definition here, the number of clusters for n data points is less than k, and in fact, if we chose A appropriately and n appropriately, it could be quite a bit less than k. Certainly when we chose A equals 0.01, it was quite a bit less. Two, I want to highlight the fact that the number of clusters was random. right? I mean, this was true as soon as you got to the second data point. The first data point, it's not random, there's one cluster. That will always be true. But as soon as you got to the second data point, we could have one or we could have two clusters. There is a non-zero probability of either one of them. And that just becomes more true as we get more data points. There's always some probability that is non-zero, that all of the data points belong to exactly the same cluster. There's a different probability on every number of clusters that we could have had. So that is a random variable. And two, we definitely saw in all of these cases that the number of clusters grows with that. Certainly it can't decrease. Okay, so this great point was made in the audience that it is difficult to choose a finite k in advance. What if I actually want to keep up this growth? You know, I'm doing species sampling or something like that, and I'm looking at images, and I want to see the unique different sorts of objects that could be in those images, and I want to always have this growth mode. So there are various problems I can have. One, you know, I just don't know k, so I'm afraid that if I choose one, that I'm going to run into it eventually. And there really is a trade-off here. I mean, I can't just choose k to be 1,000,000 and think that's going to be okay. In a modern big data world, you can get to 1,000,000 pretty quickly. How do you know what's the right k? And there's a computational trade-off here too. The larger k you get, the more computational power you have to spend when you're ultimately doing inference. It's difficult to infer, so k is really easy to infer when you have lots of data points per cluster. You know, when I have 3 clusters that are really well defined like this, you know, I eventually sort of say, hey, look, there's 3 blocks. I know how many blocks there are, it's 3. But when I haven't even gotten one data point per cluster, it might be really hard for me to predict the k that I'm ultimately going to get to. So maybe I do think it's finite and that it's out there, but it's going to be difficult for me to say what that is in advance, again, even using some sort of inference technique. And again, I might have streaming data, and so I can't say, oh, well, this k will work fine for today, because what if I wanted to work fine for tomorrow? What if I needed to work fine for a year in my application? So in all of these cases, something that we might consider is instead of fixing k, setting k, the number of components, not the number of clusters, to infinity. Okay, well, now we've got ourselves in a little bit of a bind. How do we generate infinity frequencies that sum to 1, that are random and have nice properties? We know how to generate 2 frequencies, the beta distribution. We know how to generate a positive, strictly fixed number of frequencies, a Dirichlet distribution. But how do we generate an infinity of frequencies that sum to 1? Seems like a tough problem. Well, in order to get at a solution to that problem, let me tell you another way that I could have generated a Dirichlet distribution. I mean, technically speaking, I haven't told you any way that I could generate a Dirichlet distribution. So in some sense, this might be the first way. But there are other ways to generate a Dirichlet distribution. But this is the one that I'm going to tell you. So, okay, I'm interested in generating a Dirichlet distributed vector. Row 1, row 2, row 3, etc. And it's going to look like this. Here's my cartoon again. Unit interval 0 to 1, from row 1 to row 4. Well, here is a fun fact about Dirichlet distributions that I encourage you as an exercise to drive on your own. That if row 1 to row k is Dirichlet distributed, with parameters a1 to ak, then row 1 has a beta distribution. And it has a beta distribution with the following parameters. The first parameter is a1, the first parameter of the Dirichlet. And the second parameter is the sum of all the parameters of the Dirichlet minus a1. Okay, here's another fun fact about Dirichlet distributions. Row 1, the first probability or frequency in this Dirichlet distribution, is independent of the remaining frequencies when I normalize them back onto the unit interval. So what's happening here? What's happening is, I'm saying, take row 1, that's a random variable. Now, take the remaining frequencies or probabilities that are generated by the Dirichlet distribution and stretch them out so that they're on the unit interval. So that's what this dividing by 1 minus row 1 is doing. It's stretching it out so that they're on the unit interval again. In that case, these two quantities are independent of each other. They're independent random variables. We can consider that another exercise, and in fact, when I do that, this remaining set of quantities, rho 2 to rho k, normalized, is Dirichlet distributed itself with parameters a2 to ak. That is magical. But it's not too crazy, right? I mean, this is giving you a distribution with k minus 1 components over 0 to 1. This is giving you a frequency between 0 and 1. And so at least this seems plausible. Yeah?
But unless I'm mistaken, it's fairly easy to convince oneself that that has to be the case. For example, by taking a move from the Dirichlet A1 to AK, and if it turns out that we get the first one, sorry, I'm not sure that makes sense, then we take another move, but I'm not sure from the rest. I'm not sure that makes sense. Sorry.
Cool. I encourage you to keep thinking about it. That is great, though. I think you'll get it. But for now, I'm just going to assume that it's true. I'm not going to prove it right now. Let's just run with this. Okay, so what is interesting about this construction then? Okay, so I can get rho 1 and then I can get the rest of my rows. But another thing that I could do is I could say, oh, I'm going to form my Dirichlet distribution recursively. I'm going to draw rho 1 from this beta distribution. Oops. Which, in the case of 4, k equals 4 will be exactly this beta distribution. So I'm going to break off this proportion of the unit interval, let's call that proportion v1, and I'm going to set rho 1 to v1. At this point, it seems like I've introduced extra notation for no reason, but you'll see in a moment why. And now what I'm going to do is I'm going to treat the rest of this as though it is a unit interval. Everything that's not rho 1. And I'm going to recursively apply this formula. I'm going to break off another proportion of what's my new Dirichlet distribution. So then I know that my rho 2 is equal to 1 minus v1. That comes from this renormalization so that everything went on the unit interval, times the proportion that I broke off this time. And I can do this again, break off another proportion of what remains, and then finally I'll just set the final mass to be 1 minus everything else. Okay, so why is this stick breaking? Well, you can think of the unit interval 0 to 1 as a stick, just a stick of probability, and we're breaking off bits of the stick at each time. So this is another way that you could have drawn a Dirichlet distribution, or it's a way that you could have drawn a Dirichlet distribution. If all you had at hand was beta distributions, this would get you to your Dirichlet distribution, your Dirichlet distributed random variable rho 1 to rho 4. And what I want to suggest is that maybe this is a great way to get at our original goal, which was to get a k equals infinity set of positive frequencies, if we just don't stop. So these ellipses down here indicate me not stopping. Yes?
What do you do if someone goes to infinity?
There is no set of a1 to a infinity that I have introduced yet. But that question will actually oddly make sense in a couple of slides, and then we can talk about it. I'm sorry, could you repeat the question a little bit louder?
Is it impossible to have all A equals infinity and lots of A equals infinity?
Okay, so both of the questions I think were essentially, what happens if the sum of the AK go to infinity? And at this point, I actually haven't really defined what I'm about to do. I've just said sort of like, oh, I'm going to keep breaking off proportions of my unit interval, but in an ill-defined way so far. So how about I define what I'm going to do, and then your questions actually will be totally reasonable, but let me define it first so that we're all on the same page. Okay, so what I'm going to do now is exactly what I did before. I'm going to break off proportions of the unit interval. And now, instead of saying that, oh, my beta parameters are determined by something that I start off with, I'm just going to put in any parameters. I'm going to call them A1 and B1. And at this point, it doesn't matter what they are, but as these observations sort of foretold, it will matter. Okay, so beta is going to give me some number between 0 and 1. It's going to be a fraction of the interval, so I can break it off. Done. I've broken off this part of the state. And I can do this again. I can say, oh, I've got another beta random variable. Again, for the moment, I'm just going to put in some arbitrary parameters. But it's going to be some number between 0 and 1, and so I can break it off again. And I can just keep doing this. And no one can stop me. And I just keep breaking off these proportions between 0 and 1, and I say that my corresponding row is everything I haven't broken off so far, so that's what this part represents, times the next fraction that I break off. And so long as these A's and B's give me a proper beta distribution, so long as they're greater than 0, I will definitely get something that adds up to less than 1 here. So the challenge here is getting something that actually adds up to 1 and doesn't have sort of extra mass hanging around at the end. And for that, if you want to know the exact set of constraints, well, first of all, I recommend that you consider deriving them yourself. But if you want to look at one particular set of answers, check out this Ishwaran and James paper from 2001. Now, there is a set of constraints on the A's and B's that is quite general. But I'm not going to get into it, and this is the reason why I don't want an infinity of parameters. I already have this infinity to deal with, this row 1, row 2, row 3, out to infinity. I don't need another 2 sets of infinities. That's too many infinities. I'm going to have to learn all of these parameters or do something with them or set them. I mean, these are sort of hyperparameters, so I'm probably going to have to set them. And so it's going to be a lot easier for me if I don't have so many parameters. And so I'm just going to set the A's to 0 and the B's to alpha. Or sorry, the A's to 1 and the B's to alpha. Yeah. Can't set the A's to 0. That would be bad. That would not be a proper beta distribution. Okay, so what's going on here? Well, so if I set the A's to 1, then somehow the B's are just telling me, how big that second part is relative to the A's. So that doesn't seem too crazy. I have this control over sort of, we talked about the beta distribution a lot. We talked about how if the second parameter is bigger, then I expect that, the second sort of part of the beta distribution is going to be larger than the second part of the draw. If the second parameter is smaller, I expect the first part of the draw will be larger. And so this gives me, some level of control. And it leaves me at the end of the day with just one parameter, which is convenient. So when I make this setting, when I say that all the A's are 1, all the B's are alpha, I get what's known as Dirichlet process stick breaking, or alternatively, if I want to say that these rows, this infinite vector now of rows, row 1, row 2, row 3, etc., has some distribution, we say that that distribution is the GEM distribution with parameter alpha. And that alpha parameter is often called the concentration parameter of the Dirichlet distribution, of the Dirichlet process. Okay, GEM is named after 3 individuals, Griffiths, Engen, and McCloskey. It turns out that this was basically discovered and created in the early ecology literature, which is kind of fascinating. So this McCloskey, 1965, this is McCloskey's thesis, and it's the only thing that I've ever had to get from an actual microfiche and delivered from another library, which is, I don't know, I thought that was kind of fun. Engen also in the ecology literature, and then Ewan's paper cites some correspondence or some unpublished manuscript with Griffiths, and so he's the one who names this Griffiths-Engen-McCloskey distribution. There's also a sort of fascinating thing that goes on in Bayesian nonparametrics that in both ecology and the probability theory literature, there was a lot of work done before the 80s, sort of creating the theoretical foundations of Dirichlet processes and Chinese restaurant processes and things like that. And then basically in the 80s and 90s, Markov chain Monte Carlo was born. Modern computational tools were born. Suddenly things, could actually be done on computers. And so you saw this resurgence, or even this totally new way of doing things that really depended on actually being able to calculate posteriors and do things on computers. And that's what we see in the sort of references from the 90s and forwards. And so you'll often see this particular 1994 reference given in in reference to this sort of stick breaking that's going on. Now I want to say, we've made this choice of the A's being 1 and the B's being alpha. This is not the only choice that you would actually necessarily make in practice, and hopefully we'll talk a little bit more about that probably towards the very end. But certainly this choice is the canonical choice. It's the choice that will lead us to the Dirichlet process, which we haven't quite defined at this point. Any more questions about what we've done so far? Yes?
Isn't this a 1A2 more general than before? But, if you have the same factors before, it should be then A2 plus A2 should be 1. Yeah,
it's different than before. Because if we did what we did before, then we couldn't go to infinity. We would have to stop at some point. Because otherwise we wouldn't have a well-defined Dirichlet distribution. So in some sense, you could say that we were inspired by this construction of the Dirichlet distribution, but this is just a fundamentally different thing. Okay, great. So at the end of the day, this is what we have. We have this recursive stick-breaking representation that gives us the Griffiths-Engel-McCloskey or GEM distribution over this countably infinite set of frequencies, a random distribution. So what have we done so far? Well, we use the beta distribution to get a random distribution over 1 and 2. We use the Dirichlet distribution to get a random distribution over 1, 2, up to k, where in my cartoon k equals 4. And we use the GEM distribution to get a random distribution over the positive integers. Certainly we've seen distributions over the positive integers before. I mean, you just look at something like a Poisson or a negative binomial or things like that. But here we have a random distribution over the positive integers, because in general we don't know, if we're doing something like mixture modeling, what the proportion of data points in each cluster is. And so, to some extent, we're starting to answer the questions that were posed in the beginning. How can I have an infinity of parameters and yet a growing number of parameters? Well, I can have an infinity of parameters because those are the components. I have an infinity of components here. And when I start drawing the cluster assignments, when I say that my first cluster, my data point for my first, or my cluster for my first data point is going to be cluster 1 with probability row 1, cluster 2 with probability row 2, cluster 3 with probability row 3, I'm just going to be drawing one assignment. There's going to be a finite number of clusters for any finite number of data points. And that number of clusters will grow as the number of data points grows. So we're starting to see this idea of having an infinite number of parameters in the sense of an infinite number of components. They're latent parameters. They're not necessarily instantiated in the data. They're sort of waiting in the wings. But a growing number of parameters in the sense of the parameters that I actually see in my data, that I can infer from my data, that are present in the data, the growing complexity of the model. So we're going to take a break in a moment, and I understand it's a pretty short break. So in some sense, you can think of these exercises at this point as being for down the road when you have extra time in the afternoon or after this class. And I'll highlight some that you might think about during the break if you do have time. So one particularly straightforward one is we proved that the beta and the Dirichlet were conjugate to the categorical. And so you want to just make sure that you completely understand that proof and convince yourself what the posterior is after n data points. So we just did one data point. We just did one draw, one categorical draw. What if you do n IID conditional on the frequencies categorical draws? At some point, try proving this for yourself. This is not going to be something that we draw on in the rest of the talk, so this could be something for later when you have more time. Again, coding your own GEM simulator, that could also be something for later, but something you might want to think about is how you would do it and what might be challenging about doing it. And in particular, the whole point of this drawing row is that eventually we're going to draw cluster indicators from row. We're going to draw for each data point which cluster it belongs from, conditional on row. And so you want to think about why this combination is going to be hard and what you might do to get around whatever that difficulty is. Some food for thought. And then when you do this, you're going to get some sort of growth in the number of clusters, and you want to sort of think to yourself, how does this growth, as the number of data points grows, compare to the growth that we saw in the k equals 1,000 case? What's different? What's the same? How do things change? And also, how do you change with alpha? So how does alpha affect this? So this is something that you can also think about just a little bit as a thought exercise in the meantime. Okay, so let's break for about 15 minutes, and then I guess we'll be back here at 10:45. Great.